All right, so in our last example, we looked at how to make a ball appear to fall with gravity and to bounce, and it's pretty convincing with just a few numbers that we can change kind of the behavior of this. We can change the level of bounciness so that it appears to be kind of like a different sort of material. And this is pretty cool. Like, I mean, there's hardly any code here, and it's able to create this very believable kind of thing. Ball bounciness gets really complicated, or like any simulation, you can go as complicated as you want. I'd recommend, I'll put a link to this article in the description, but this article on Wikipedia on bouncing ball, I love that Wikipedia is amazing. There's an article called Bouncing Ball. And I mean, this is like a really detailed, thoughtful like way of like explaining all the factors, or some of, I'm sure there's more, that go into determining how a ball bounces, like the Magnus effect, the rotation of the ball as it's falling, the buoyancy of it, its impact, you know, all, it's really great. I don't understand most of this. I think it's pretty cool. Even sports regulations over the bounciness of balls, I think it's really amazing. So I'll put a link to this if you want to go deep. This is a good example of something so simple. You can go really deep. But let's talk about first how we can change our example here to work a little bit better in terms of code. So our x and our y position here are defined as separate variables. And for some things that may work totally fine, but I think we may want to, or it's going to be really helpful to use the PVector class. And actually, let me pull up here the reference, because this is really helpful. So PVector is a class. It's part of the processing library. You can also get much of this in P5.js under the createVector command. But PVector stores either a two-dimensional or a three-dimensional position. So if you were to be working in 3D, you can also have Z. But what it really provides, so I mean, one of the nice things is that we can store the x and y together as a single variable. But the other thing it provides is a whole bunch of commands or math, vector math, that work really well and are very much optimized too for a lot of this stuff. So we're going to see just some of these. Others you may run across in some examples. But the PVector is really, really helpful this way. So instead of keeping track of our position using a separate x and y variable, we're going to do a PVector called position. So I can get rid of this. We're also going to make, so a PVector can be a position, but a PVector can also be a force. So we can define the amount of a force like gravity or speed or wind, also using a PVector. So I'm going to create one called gravity and one for speed. So now I can delete this and I can delete that. And we're going to talk in a little bit about why bounciness is not a PVector. But so now in our setup here, we're going to start, I'm going to make a local variable called x just to sort of like initiate the position here. I'm going to set x to diameter divided by 2. And actually, so let's start by recreating this the way we had it before. In a minute, we're going to move the ball over and have it actually bounce not only up and down, but side to side. But let's start it with x at width divided by 2 and y at diameter divided by 2. And you wouldn't need to make these variables, but I think it makes our code a little more readable. And then we can say position equals new PVector, and then the x and the y position. And yeah, like I said, you don't need to create those x and y variables here. You can do it here. And the reason that we're initializing this PVector in the setup is in part because we're accessing the width variable, but also, again, with the key press down here, this allows us to reset it using our keyboard. And then our speed is going to be, speed and gravity are going to be similar kind of thing here. So I'm going to say gravity equals, new PVector 0. Gravity is only pulling down. It's not pulling left to right, and 0.5. Now, again, gravity we could leave as a single value because there's no x direction force, but we'll see in a minute. This actually makes it a little easier with the PVector math that we can do. And then speed new PVector. And our speed, we're going to start at 0, 0. In a little bit, we'll actually change this so that the speed has some left-to-right motion as well, like it was sort of thrown. So we don't need to change anything else then in the setup. Our background, though, or sorry, our draw needs to change because we don't have a y, and speed and gravity are p-vectors, not regular numbers now. So the first thing that we want to do is change the speed, have acceleration due to gravity. So I can say speed dot add gravity. And this is one of those great examples of p-vector math operations that are really easy. In fact, in some ways, I think this is easier to read because it's just one line. It's really simple. I'm adding gravity to the speed value, and behind the scenes processing does all that work for us. And then similarly, so our speed is accelerating over time, then our position dot add speed. So now we've changed the speed over time and the position to match that speed. And for recreating our previous example, where we were just using standard numbers to represent the x and y and the speed and the gravity, this doesn't really save us much. But if the speed is going to be changing, as we'll see in a little bit, left to right, now we're saving 2 extra lines of code where we would maybe have to change the x and the y position and things like that. And if you get more forces involved, like attraction or friction or things like that, then you can start to see where this really gets super helpful. Now, because we don't have a y position directly, we can't just use y here, but we can access this separately, the x and the y parts of the p-vector using the dot syntax, just like we do in a class. So I can say position dot y instead of position. So this is that bounce off of the bottom. So if it's hitting the bottom of the screen, then I can say position dot y equals height divided by, or height minus diameter divided by 2, so that it's sort of like not getting caught in the bottom like we saw in the previous example. And then we need to change the speed of the y direction, so our bounce up and down with the bounciness. So I'm also going to say speed dot y. So that's our bounce. We're just sort of adding the names of the p-vector to these things. And then similarly down here for this ellipse, I need to say position dot x, position dot y. Let's try running it, make sure we didn't mess anything up. That looks pretty good. And it should look exactly the same as the previous example. So we didn't really change how anything works here. We're just changing, or we're not changing any of the parameters. We're just changing kind of like how we're storing those values. So this looks pretty cool. Let's now have the ball not just bounce up and down, but move side to side as it's going. And to do that, we can, let's start our x position instead of at width divided by 2. Let's make it diameter divided by 2. Then it's going to show up over here. And in fact, if we just run this, we should see our balls over here. And now we can change the speed in the x direction. So the speed in the y direction is going to start at 0, just like if you were to release a ball from your hand, you wouldn't see it, it wouldn't immediately be moving downward. But we can add speed in the x direction this way, and let's see what that does. So now our ball follows these kinds of parabolas. It goes off the screen where we can't see it, but for now at least, this is working the way we want. Hit spacebar and sort of reset that. We can change this speed to be something different and see how that changes its behavior. So now it's only has a speed of 1 in the x direction, so it's going to kind of like slow down. And now it's just going to keep rolling forever because this speed doesn't decrease. So that's the next thing that we want to change. Here, when it hits the bottom, we have been decreasing the bounce overall of the ball up and down, which makes a lot of sense sort of like from our real world experience of bouncing things. But balls don't just keep kind of rolling forever. Their motion that way is also slowed down, and that's because of friction and things like that. So I'm going to say speed.x times equals bounciness. Now, you might be thinking, well, why isn't it negative bounciness? Let's see what this looks like. So now our ball, you can see, is like moving over by less and less each frame until eventually it's going to settle in and be still. We can move the speed back up to 3. And is it going to go off screen? It's going off screen. But we could try changing this, and you'll see that it slows down. If it might seem intuitive that we would want bounciness to be negative as well, because it's negative for our y direction. But if we do that, I mean, it might be what you're after. The ball is going to bounce one way and then the other way and then back and forth and back and forth, which is not super, that's not what we were expecting, sort of a natural behavior. But instead, so just in the same way that this bounciness is reducing the amount by which it's able to go up every frame, the x being multiplied by bounciness is slowly, because bounciness is less than 1, that speed is getting smaller and smaller and smaller and smaller until basically it's 0 and this doesn't move anymore, which is pretty cool. So the real changes that we made here are defining our position, our gravity, and our speed by PVectors rather than individual numbers, which makes it easier to define more complex sorts of things. So now instead of having to have a speed x and a speed y variable and add speed x and speed y, etc., etc., it's much more compact. It's, I think, much more readable. So now we can change a value and see how it affects the overall kind of system. And the other change, excuse me, is that we've added motion left to right here, which is pretty great. And again, it would make sense to have this system, our ball sort of like wrapped up in a class. We're going to get to that in a couple of videos where you're going to see how we might kind of do that. And I think that would be rather straightforward to do.